Hey, thanks for tuning into my talk, and thanks to the organizers for putting this conference together. I'm going to be talking about cosmological parameter estimation with a new BBN code called LINX. So the goal of this project was to develop a fast code for BBN that's suitable for estimation of cosmological parameters. So in other words, we want to put BBN analyses on the same footing as CMB analyses. So when you do a CMB analysis, you can use tools like PLIC and CLASS to do these really detailed statistical analyses of whatever model you're trying to test. On the BBN side, there's not quite a tool that allows you to do the same, and certainly not in conjunction with some of the CMB codes. And so we were trying to fill that gap. BBN can provide a really powerful probe of both new physics and just lambda CDM. Determinations of omega B, for example, from BBN are approaching the precision of the CMB. And more importantly, it provides an independent epoch of cosmology that you can use to test whatever model you're interested in. And so we felt it was really important to be able to do BBN analyses at the same level as these CMB analyses. So the rest of the talk will be organized as follows. I'll start by talking about methods, so I'll talk specifically about LINX and what went into its development. And then I'll talk about some of the physics applications, some of the new analyses you can do now that we have this new tool. So I'll start by talking about these methods. So if you've ever done a BBN analysis, the first question you've probably had to answer is which BBN code you're going to use. There's this whole landscape of BBN codes, but all of these current BBN codes require you to make some kind of compromise if you ever want to do parameter estimation. So you may have used a fast code like AlterBBN or Parthenopy, but these codes have some shortcomings. So AlterBBN, for example, is a bit out of date, and their treatment of neutrino decoupling is not state-of-the-art. Parthenopy is not quite set up for parameter estimation, or not at the level that we argue it should be done. There are also some more state-of-the-art codes that are a bit slower. So Premot, for example, is extremely accurate, has the largest BBN network out of any code you can currently use, but it's written in Mathematica, and that means it's just really slow. Additionally, there's Primordial. So Primordial is sort of like Premot, but translated to Python. So it inherits a lot of Premot's accuracy. And they also added a lot of new options for new physics. They're set up like Premot for parameter estimation, but it's just a little bit too slow. If you're trying to do MCMC or a similar sampling method where you're calling the code millions of times, 10 seconds per evaluation is still just too slow. So we came along and wrote LINX. LINX stands for Light Isotope Nucleosynthesis in JAX, and so we add JAX to the picture to make things run a lot faster, and I'll talk more about JAX on the next slide if you're not familiar with it. So we inherit the accuracy of Premot and Primordial, but our main advantage here is that we're fast enough for MCMC methods. So just in case you're not familiar with JAX, I thought I would spend a slide singing its praises. JAX is AutoGrad and XLA. So AutoGrad automatically gives you your gradients. So say you wrote a likelihood function using JAX, you would automatically get the gradient of that likelihood function. And this opens up new methods for parameter estimation. So things like HMC or SVI, these sort of sampling methods that call significantly fewer points than methods like MCMC. And then XLA is accelerated linear algebra, which is sort of the foundation that JAX is running on to run so fast. It's nice for physicists because it looks and feels like NumPy. So you would just open up a Python script, and instead of importing NumPy, you would just import jax.numpy. And so the coding feels very familiar. It's easy to read the way that you're used to. And then you can also run it on CPU or GPU, or if you have access to a TPU, it's also very easy to run out of the box on this different hardware. In particular, JAX compiles, so it uses just-in-time compilation. So the first evaluation of your JAX code will be a bit slow, and then subsequent evaluations will be lightning fast. So to give you a little demonstration, we put this little animation together. So each of the curves here is the abundance of some different elements that are forming during BBN. It's normalized to the baryon density. We're showing each of these curves as a function of time during BBN or as a function of the photon temperature. And then the animation was showing what happens to these curves as you vary the baryon to photon ratio. And I can show it again. So it took us about a minute to compile the code to generate this, and then just 2 seconds to get all of the data we needed to get this animation. For comparison, it took us about 10 minutes to generate the animation with Matplotlib, and so we are running very fast. To be a little more specific about the actual improvements that we made to the codes, I want to be clear, we did not cut any corners to get a fast code. We're not introducing any new approximations, we're not losing out on accuracy, we are just as accurate as those other codes I mentioned earlier. We're also not an emulator. You do not need to retrain LINX for different new physics models. It should work for you right out of the box and run the first principles calculations every time. We are faster, and this is largely because we translated to JAX. And then we've also kept an eye towards things like new physics or things like readability and documentation so that lots of people can use the code very easily. Finally, our code is also differentiable. I won't be talking too much about the differentiability more in this talk. If folks are interested, I'm happy to talk about it later during the discussion. So that's everything I wanted to say about the code. Now I can get to what I think is the really exciting part, the new physics analyses that we can do now that we have this new tool. So I mentioned a few slides ago, there's these, when we're trying to do parameter estimation, there's not always an option to vary the BBN nuisance parameters. And what are these BBN nuisance parameters? So the main input to BBN codes is a reaction network. This is data that comes from experimental physics. It includes rates for all reactions in the network. And so nuclear physicists go out and they measure these things. And so you can get text files that look like this that come along with BBN codes. So for each reaction in the network, this is just showing one reaction. You'll have as a function of temperature, and this will go all the way up to 10 MeV, this S factor, which is closely related to the cross-section for the reaction, and then there's also this uncertainty that they provide as well. So because we have this uncertainty, this means we need to sample the rates as nuisance parameters. You can't just use the central values and say you're getting an accurate estimate of your error bars. You really also need to be including this uncertainty when you do your sampling. So previous codes, and in particular, I'm going to focus on parthenopy, mostly because that's what Planck uses to do their joint CMB and BBN analyses. So parthenopy is not quite set up to vary the nuisance parameters in the way that we argue you should. They do something called linear covariance estimation, and they can use this to sort of get an idea of what the theory uncertainty or the prediction uncertainty should be. So they have a likelihood. So for helium, in case you're not familiar with this notation, YP is the helium-4 mass fraction. And then they'll also add a deuterium piece, which is normalized to hydrogen. They'll get some estimate for the theory uncertainty on their helium prediction and on their deuterium prediction. But the way they'll do this is they'll sort of guess at where omega B and N effective are going to end up in their posteriors, and they will try to estimate the theory uncertainty there, and then they will use that theory uncertainty for all of the parameter space that they're sampling. But we found that that theory uncertainty is not constant. And so what I'm showing here is that as a function of N effective and omega B, the uncertainty on the deuterium prediction in particular can vary by more than 30%. And so what we argue you should do instead is to sample your BBN nuisance parameters along with your model parameters. So for each of the reaction rates in your network, you will have one nuisance parameter, and you should also be sampling that nuisance parameter. And this is possible with LINX. Okay, so what happens when you do this? So what I'm showing here is results from using a constant theory uncertainty versus actually marginalizing over the rates with LINX. So let's focus in on this constant theory uncertainty. These are the error bars showed in this sort of salmon color. These are, again, calculated using this sort of constant theory uncertainty that's calculated at just this one point. Meanwhile, you can see in this darker color that when you actually marginalize over the nuisance parameters using LINX, you can actually get a reduction in the error bars. So I want to specifically draw your attention over to this data point on the left. For this analysis, we got a posterior for omega B by holding an effective fixed. So we said, let's just do lambda CDM, let's hold an effective to 3.046, and let's get a posterior for omega B. And when we do that and we marginalize over the rates, we found that we got something pretty different from these previous analyses. So this is comparing to the sort of analysis that's done in Mills-Schoenberg's 2024 baryon abundance update. But this is also the procedure that is used in Planck. So I've been talking a lot about Planck um, because we're trying to build up to this CMB and BBN joint analysis that we want to do really consistently, varying all of our nuisance parameters. So let me talk a little bit more about what we want to see out of these joint constraints. So we argue that you should do the following if you're trying to do a joint fit. You'll start with these common model parameters. Let's say you want to vary both omega B and N effective, and you'll pass them into both your BBN and your CMB codes. Let's start with the BBN side. So we will also we'll also sample these BBN nuisance parameters. So for each reaction in the network, we will have one additional input, which is another BBN nuisance parameter. We'll pass all of this into our solver, in our case it's LINX, and we'll get predictions for deuterium and helium-4. This can go into a joint likelihood like the one I was showing on the previous slide. Meanwhile, you take your prediction for helium-4 from your BBN code and you pass it into your CMB input. Now, note that this prediction for helium-4 is also encoding some of the information about the nuisance parameters that you sampled. And so everything here is totally consistent now. So now you have your CMB input. It has information from BBN that's consistent with the parameters that you sampled. And then you might also have some CMB nuisance parameters if you choose to sample those. You pass those through your Boltzmann solver. We used class to get some CLs, and then you can construct a CMB likelihood. We used click and plick for that. So when you do all of this, you can get a huge posterior that looks like this. So there's not much that's quantitative that we can really extract from this plot, but I want to show the parameters that we can sample now. So we can sample our cosmological parameters. This includes N effective and also omega B and the other CMB parameters. And then in orange, I'm showing that we can also sample the CMB nuisance parameters, which is also run by plick and click. But we're also able to vary the BBN nuisance parameters alongside the CMB parameters for the first time. And so we're showing in yellow here, these are the individual reaction rates that we sampled. And then we also vary the neutron lifetime as a BBN nuisance parameter. To generate this posterior, it took us about 2 days on 192 cores. We used nested sampling, so if you're not familiar, it's sort of like MCMC, but it's easier to parallelize and it's better for high dimensional and multimodal posteriors. So this is still sort of resource intensive, but I want to point out that our long runtime is now dominated by class, where previously this kind of analysis was impossible because there was no BBN code that allowed it. So now if you want an even faster joint analysis, we actually need a faster Boltzmann solver. So with that, I can conclude. We have this new BBN code. It's called LINX, and it leverages the speed and differentiability offered by JAX. So that means it's fast, and we also are trying to make it really flexible. This means that there are new physics analyses that were not possible before that we can now do. So we can incorporate the BBN nuisance parameters and do CMB and BBN joint analyses. So we have brought the BBN side of these analyses up to the same level as the CMB side. We're really excited to start doing some more new physics with this code. So in the future, we're looking towards model-independent explorations of thermodynamic histories, so ways to constrain new physics that don't depend on a particular model. And we're also really excited to be releasing our code, if not this month, then hopefully next month. So do keep an eye out for that. I'm really excited to see what the community will do with it. So thanks for tuning in.